introduction to robotics and AI. Now let's see the recent advances that we have in the last decade. First, what is our goal? We want to design smart robots. What do we need from a smart robot? Well, we needed to have proper vision in order to understand what it's seeing. We also would like it to understand when we're talking to it, so we'd like it to be able to do language understanding and also be able to reply to us, so generate text and generate speech. Also, it would be pretty useful if it was able to reason and act. And finally, in terms of hardware, we would like it to have hardware in order to do object manipulation and movement. Let's see what we did in terms of progress in the last decade in terms of computer vision. First, many of you probably have seen that computers are starting to be very good at face recognition. So for example, in your phone, when you take lots of pictures, your phone may be able to group the pictures of your friends together, and now you can search your friend and pictures you have taken about them. Or also Facebook is able to tag your friends in pictures. Similarly, we can use pretty much the same techniques in order to detect diseases in medical data. So for example, in CT scans, we're able to detect certain tumors, or also in the eyes, we can detect certain diseases from images of the eyes. And finally, we can also segment objects in natural data. So for example, this picture, we can see that here there's a car and here there's a dog. A pretty direct application of this last problem that we solved is self-driving cars. Many people don't know that actually self-driving cars were starting already in the 80s, but they had two main issues. You can see that these sensors were not very good, but now we have very good sensors that have very detailed 3D information and very high resolution images, and also this progress in computer vision. And you can see here the images coming out of a self-driving car. It's continuously monitoring its environment and is able to detect all the cars and all the pedestrians with very, very high accuracy. In this way, then it uses this to not collide with them and plan directions. However, there are some challenges currently in self-driving. You have probably seen that there's many cars doing self-driving in highways, like for example, Tesla self-driving cars, but self-driving in cities is much harder. One issue as well is that we need many nines of accuracy. So we may need 99.999% accuracy, not just 99%. Because for self-driving cars to be feasible, we need them to be better than humans, and humans kind of need to drive to the moon and back 2 times before getting into an accident, and even 150 times back to the moon and back before getting into a deadly crash. So we're actually pretty good drivers. So in particular, if we'd like to be such a good driver, we may need very advanced AI. The reason being is that maybe we need to be able to plan against in very complex circumstances. Also, we need to interact with humans, and since humans are very smart, in order to predict them, we also need to be relatively smart. And finally, if we want to get all these lines of accuracy, we have to be able to deal with very, very uncommon situations. Take the following example, where we have a Google self-driving car, and here there is an old lady in a wheelchair with a broom chasing a duck. Where else are you going to see such a crazy example? And the self-driving car has to be able to obviously see this for the first time and react appropriately. Or here is some people jumping around the car, just trying to play around, and we're trying to fool the car. And in this third example, there is multiple cars going in the wrong direction. And the self-driving car has to notice that and obviously not collide with them, even if it would be legal for it to go to the right. Cool, now we have seen the progress in vision, let's go on to the progress in language understanding. Maybe you have noticed as well that Google Translate or other translating services have gotten very good at translation in the last 10 years. And this is also done with deep learning technology, which again is also used in voice understanding, which is why we have our voice assistants in our homes, like Alexa, for example, that are also able to reply to us. And finally, we're starting to get better at generating text. We cannot generate long paragraphs of text without losing consistency. So, for example, AIs can still generate feasible books, but we're starting to be able to generate short sentences and paragraphs. Not only that, but the cool thing is that we can start to combine this, for example, this vision neural network in order to understand this image here with the text neural network. So we can actually say, okay, interpret this image with an image neural network, and then feed it to a text neural network that kind of outputs a description of this image with a sentence, and not just classifying objects. Now let's move on to describing how we can learn to act, which is what we were referring before as reinforcement learning. In this case, we have a robot, and we have the environment. And the robot can act on the environment via some action, and then it will sense through its camera what the environment is, what its effect of the action was on the environment. And also we have our cookie. We will say a reward if you did well, and no cookie if you did badly. A very pragmatic example of this is games. In games, we have our joystick, and then we have the environment, and then we have kind of the image of the game, and as a reward, we just have the score of the game. And so, for example, in 2014 or 15, machines learned to play Atari games, where now we are taking the image as an input, we feed it to a neural network, and now instead of classifying whether it's a cat or a dog, what we do is try to predict what's the best action to do in a certain situation. Similarly, we can use the same technology to be able to do low-level robotic tasks, like using this ball, for example, or also play more complex video games like StarCraft this last year. As a very instructive example, let's compare how we were able to solve chess 20 years ago with how we solved Go a few years ago. Deep Blue in 1997 beat Gary Kasparov at chess, and the way they did that was by a team of human experts, both programming experts and chess experts talking to each other and generating some piece of code that was able to evaluate any board position in chess. So for example, something very simple you could do is say, okay, the queen is worth 9 points, and so if someone has the queen and the other one doesn't have the queen, 9 points to you. And things like this, but instead of just one rule, you had thousands of rules, and eventually you are able to assess pretty accurately whether a board position is promising or not. And then you have kind of a huge search into the future where you evaluate every possible move that I could do, then the other opponent could do, and then eventually you pick the future you like the best. In contrast, and then this requires quite a bit of human knowledge in order to code this evaluation function. In contrast, the way that Go was solved was by having kind of the AI play against a copy of itself for thousands or millions of times. At the beginning it was random, but then it started learning that some actions lead to victory more than others, and then in this way it learned how to play Go. And so no human knowledge was required. Not only that since we don't need human knowledge, we can almost the same code can now learn chess or learn shogi. Now, the same algorithm can solve multiple games, and again, just board games in this case, but it requires thousands of hours of training, or even more than that. And if we get a new task, such as a new board game, for example, we have to start from scratch. There is no transfer that happens between tasks. Now that we have explored the progress in software, Maria will talk about the progress in hardware.
Okay, so we have seen a lot of progress in software and computers, but how does this translate to robots? And usually when people think about robots and think about Boston Dynamics and say, hey, have you seen this video? Because it's super cool. Like this is a robot from Boston Dynamics, and it can do amazing things. I would bet some of us would struggle with this, I would at least. And this looks kind of human, right? I mean, the motions are so natural. And it's powerful. But then people ask me, how close is this to kill me? Is this really smart? Is this going to come and do anything? And actually, what it is quite amazing, it's mostly not machine learning. It's actually hardware and controls. So that means the motors, the joints, the thing that is building this robot is amazing. The way it interacts with the wall through sensors and the robot itself is controls, and it's also very powerful. But there is no real machine learning or intelligence embedded into it. It's more like a very, very smart machine that can take actions, but not to so much think about how the world is changing because of these actions. But it's making a lot of progress, and I would say it's one of the most amazing progresses that we have seen in robots. Other ones are drones, and also surgical instruments, and one of them is Da Vinci. And those are making also a lot of progress. But actually, if you look inside, there's again not much artificial intelligence. Most of them are teleoperated, though there is a human analyst telling where are the big challenges, where are the big decisions that need to be taken. So the question is, we have seen a lot of progress on machine learning, artificial intelligence. There is a lot of progress on robotics on the side of controls and hardware. How do we merge them together? For me, one of the key cases that we have seen in robots is when Amazon actually entered into the world of robotics. And Amazon, when you think about it, it's just a big place with a lot of employees and a lot of warehouses that they are really big. So the tasks that humans had to do were, well, you need to go and find that object because some customer has ordered it. So you need to go through all those big places and find a shelf that contains that object. And you need to pick it up and put it inside the box. So that's challenging. And Amazon said, okay, what if we invest in robots? And the first thing that they do was investing in this killer system. Those are mobile platforms that go underneath the shelf, lift it, and bring it to an operator. So now at least people don't have to go into Amazon and actually go all the way, pick the object, and go back. That's not on my robots. But then there is one thing missing, which is a human still has to go into the shelf, take that object, put it inside of a box, so then you can actually get it to your house. And they said, let's ask people that is doing robotics how to solve this problem, because we have no clue. And this is how they proposed to the robotics community the Amazon Robotic Challenge, when they said, your job is going to be the following to the researchers. We're going to give you a bin full of objects, and you have to devise a system that autonomously can just go and take those objects and put them inside boxes. So exactly the work that they needed to add into their warehouses. So we were a team, Ferran and I, other people from MIT and Princeton, that decided to build a setup like this one to actually compete in the challenge. And when you think about the challenges, which one are those? Well, first of all, there's going to be the challenge of obstacles. You want to be safe. You don't want a robot that just goes and collides with everything and finally reaches the object. You need to be aware of your environment. Second, there is clutter. There is density, a lot of objects. It's not a bin where everything is sorted and well arranged. Is everything just dumped into a bin? Good luck finding whatever you need. That means that sometimes you may need to remove something so you can actually go and grab the object that you want. And finally, not all the objects are boxes. If all the objects were to be boxes, the problem would be much easier. Objects can be almost anything. They can be different weights, from very light to very heavy, from very big to very small. And that means that you have to build the same system that is going to work for all this variety of objects. And again, if they were boxes, it would be much simpler, but now you can encounter a lot of different things. So how do we solve this problem? Our team used this robot. It's really big, which means it can apply a lot of force, which means it can lift from heavy to soft objects. So it cannot really allow us to solve this for many variability of objects. Second, we need to understand the state of the world, so we need sensors. In this case, we use 12 cameras. And finally, the most important thing, because we are going to be interacting with objects, we need to make sure that the part of the robot that interacts with the objects is as powerful as possible. So for that, we devised this end effector gripper that is the one that's going to be in charge of actually contacting the objects. Let me zoom in. This is how it looks. It has a spatula, can close and open its fingers, and finally, it can deploy a suction cup that is going to be able to suck the objects when needed. So it can do some of those operations. It can just go and suck objects, but it can also grasp them with the gripper, depending, because some objects are very easy to suck, others are very easy to grasp, and some are just very hard no matter what. So you need to be able to combine those strategies. But now that you know how you're going to interact with the world, you still have some questions to solve that require you to be more intelligent. So the first one is going to be, where are you going to pick something? You are faced with a bin, where are you going to go and use your end effector? And for that, we use all the images from the cameras. We have both images and depth images. And we use a neural net to actually predict where are the regions in the bin that are more likely to give you good actions. So if you look in this image, actually some of the regions have more density. That means that they are better. And we actually can go in there and perform a grasp, as you can see in here. But now there is a second question, which is, what is this object? Because you need to put it in the Bauza, you don't want to do that wrong, because that is going to cost you money. So the next question that we need to solve is the object identity. But there actually you can make a trick. You can not just leave the object, bring it to a known position, and now you can get an image of it. Moreover, you can have some images of what are the objects that are inside the shelf. You know them. You don't have any object in the shelf. You know what object you have. So all we do is use a neural net to actually make this comparison and say, hey, this is the most similar object. This is the object you have in the hand. So now you can finally go and put it inside of a box or wherever you have to put it. Let me show you how it went. This is the context. This was us pressing a button and letting the system run. And as you will see, it can grasp many objects, but sometimes it fails. Not always, but sometimes it's just going to fail because it thinks that it's a good action, it's a good idea to go in there, but it might actually not be. So when looking at this system, we were really happy. It can solve the task autonomously, there is no human anymore involved, but it's not perfect. And that allows us to think, what is next? What are the next things that we should solve in order to make this system better? I'm just going to let it run. You will see how it's going to figure out how to grasp all the objects. But the less there is, you can see that they are in hard positions. It tries, now I think it's going to grasp the book. It succeeds, and that object is going to take a while, but finally figure out how to grasp it. So we were happy with being this part of the competition. But it also allows us to reflect what is next. We have a good system, but what should we do next? The first thing is this. I already showed you. That makes no sense, because there is so many objects on the top that you would never try to grasp it with a suction cup. What you would do instead is first remove the thing on top, and then you will be able to reach the white binder. So it's again the idea that we need intelligent planning. We need to be able to say, hey, this is the good sequence that you should follow if this is what you really want to achieve. And from all the things that we have told you before about how to solve in games and how to learn to act, we can learn better policies and better ways to act on this. But that is not yet there. The second thing is this one. As you will see, the robot is going to succeed to grasp this object. But look at it, it's not that stable. The object now is going to move inside the grasp. And that's because even though it succeeds, it's not aware that that is not stable, that is not good. If the robot would move again, the object would just fall. So again, we need to understand better how the world is changing when we act on it. And that requires better sensors and requires better control. So that if you're doing something that is not very stable, you better change your motions. Because imagine that were to be something full of water and made of glass. It's just going to fall, it's just going to break, it's going to make a mess. So you need robots to understand that not every action leads to good outcomes. But that was enough progress, so that Amazon continued the research, the robotic community continued working on this problem, but also startups decided that this was a good time to invest in these solutions. So now there are at least 4, probably even more startups working on how to deploy these systems into the industry so that this part of automation becomes possible in a more realistic scenarios. So with that, we're going to finish the second part. If you have any questions, we're happy to take them now.
Can you talk about how this looks when it's actually in a warehouse? Because this is like, I don't know, I can imagine not quite big and maybe not very convenient to stack. Like, how do you make it then smaller or not?
So maybe...
Clear question.
Oh yes, so the question was how do we actually incorporate this into an industry so that it actually makes more sense? Should it be more compact? How should it look like in an industry? I think dimensions might not be the biggest issue. What you want is reliability and repeatability. So you need to make sure that nothing is going to break, that humans are not going to get hurt if they move around it. But the size, actually, because you need robots that are strong enough to move the objects even if they are heavy, that is not the big issue. And most of the robots will look exactly the same, so you can actually stack. I think most of the warehouses would be happy. Because even if you were to have humans, you wouldn't have them all nearby, they would still need to have some volume nearby. So dimensions might not be the biggest issue, but definitely making sure that everything is reliable, that nothing is going to break, that objects are not going to fall somewhere that you cannot reach them anymore. Those are the biggest issues that they need to actually solve.